in the last lecture we have introduced the Dirac spinner. Psi, and then we have seen how it transforms under Lorentz transformation. So, under Lorentz transformation, the Dirac spinner goes like psi of x goes to e to the power minus I over 4 omega mu nu sigma mu nu acting on psi of x, where sigma mu nu is given by I over 2 commutator of gamma mu gamma nu, where the gamma mu gamma nu are the Dirac matrices they are a set of 4 by 4 matrices which satisfy this anti-commutation relation gamma mu gamma nu equal to twice eta mu nu. Then we have seen that in one particular representation known as the chiral representation, this Dirac matrix, these Dirac spinners can be written as psi L, psi R in terms of the left handed and right handed components, and the Dirac matrices in the chiral representation are given by 0 minus I 0 and gamma I equal to 0 sigma I minus sigma I 0. Is that right? Okay, so these are the Dirac matrices. However, we need not have this representation. Any representation, any set of 4 by 4 matrices which satisfy this anti-commutation relation will be good enough to represent the Dirac gamma matrices, the Dirac spinors. Then what we saw is that we can try to construct various invariants from the Dirac spinner. One of them we have seen is if we define psi bar equal to psi dagger gamma 0, then psi bar psi is actually Lorentz invariant. Then we were discussing about the Lorentz transformation property of this object psi bar gamma mu psi. So, let us see how this object transforms under Lorentz transformation. This transforms like psi bar goes to psi bar S lambda inverse and then gamma mu and the psi goes to S lambda psi of x. This is how it transfers. So, what we need to do is we need to know what is this object S inverse lambda gamma mu S of lambda. We can do an infinitesimal transformation where this is given by to order omega mu nu, this is 1 minus I over 4 omega mu nu sigma mu nu. Then let me write it as alpha beta gamma mu and 1 minus I over 4 omega rho sigma rho sigma. So, to order omega this looks like 1 minus I over 4 omega alpha beta sigma alpha beta gamma mu. So, there is a gamma mu to 0th order, and then this will be plus because we are considering S inverse. So, there is a plus sign here, and then you have finally minus I over 4 omega alpha beta gamma mu sigma alpha beta and all of the terms. So, this is nothing but gamma mu plus I over 4 omega alpha beta and the commutator of sigma alpha beta and gamma mu and all other term. And in the last lecture we have evaluated the commutator of sigma alpha beta and gamma mu. If you substitute it here, then what you see is you have gamma mu plus I over. So, finally, all the factors will cancel, and what you will get is delta of mu nu plus omega mu nu gamma nu. So, this is simply given by lambda mu nu gamma nu. So, this object S inverse gamma mu S is nothing but, when you make a finite transformation, this will go like lambda mu nu gamma nu. Therefore, this object here psi bar gamma mu psi under a Lorentz transformation goes like a vector, because this quantity, this is nothing but lambda mu nu psi bar gamma nu psi. So, therefore, this is a vector under Lorentz transformation. Similarly, we can construct tensors and pseudo scalars, pseudo vectors and so on under Lorentz transformation. What we are interested is, we are interested to construct a Lorentz invariant Lagrangian density. So, this should involve psi and its derivatives. You can try to construct a Lorentz invariant Lagrangian density which is quadratic in del mu psi, but it turns out that any such Lagrangian which is quadratic in del mu psi gives you various unphysical features. For example, the energy has no lower bound and so on. However, luckily we have a Lagrangian density which is first order in del mu psi, which is Lorentz invariant. So, let us try to construct a term which is first order in del mu psi and which is Lorentz invariant. To do that, consider this term psi bar gamma mu del mu psi. Okay. This quantity here, as you know, psi bar, if this del mu was not there, then this would have transformed like a vector, but we wanted to have one derivative of the field psi. So, we have inserted this del mu psi here, and then we can show that this quantity in fact is invariant under Lorentz transformation. Why? This psi bar goes to psi bar S lambda inverse, and then you have gamma mu, and del mu under Lorentz transformation goes to del mu is del over del x mu, and under Lorentz transformation this goes to del x nu over del x prime mu del over del x nu. So, this quantity is lambda inverse nu mu del nu. So, you have lambda inverse nu mu del nu of S of lambda psi. Okay. But S of lambda does not depend on space time, so I can just pull it out. What I get is psi bar S inverse lambda gamma mu lambda inverse mu nu mu and S of lambda del nu psi. This is a number. So, again the components of lambda mu nu are numbers. So, again I can pull it out. So, I have lambda inverse nu mu psi bar S inverse lambda gamma mu S of lambda psi. This quantity is, again we have computed what it is. So, I can del nu psi. So, I can substitute this here, then what I will get is lambda inverse nu mu psi bar and S inverse gamma mu psi is lambda of mu alpha gamma alpha del nu psi, and finally this is simply psi bar gamma alpha del alpha psi. So, this quantity is Lorentz invariant. So, we can have a Lagrangian density for a massive spin half field, and the Lagrangian density is given by L Dirac. The Dirac Lagrangian is psi bar I gamma mu del mu minus n psi. I have inserted a factor of I to make the Hamiltonian Hermitian, which we will soon see how the Hamiltonian density is Hermitian. It will not be Hermitian if there is no I here. So, we will take this Lagrangian density for the Dirac field, and then we will quantize the system. As usual, before quantizing this, we have to first study the plane wave solutions for this field here. Let us do various things. For example, let us try to construct the Hamiltonian density and show that the Hamiltonian is Hermitian, and then let us look for the plane wave solutions to the equation of motion. What is the equation of motion? The equation of motion is given by I gamma mu del mu minus m acting on psi equal to 0, and this is known as the Dirac equation. And we would like to study the plane wave solution to the Dirac equation, which we will do in a moment. Before that, let us try to construct the Hamiltonian. So, the conjugate momentum to the field psi is given by pi psi equal to del L over del psi dot, and this is nothing but I times psi bar gamma 0. What is pi psi bar? It's 0, right? So let us try to construct the Hamiltonian density. It is given by I psi bar gamma 0 del 0 psi minus L. So, the Hamiltonian density S is given by this, and if you substitute for the Lagrangian density, then this is I psi bar gamma 0 del 0 psi minus I psi bar gamma mu del mu psi plus m psi bar psi. So, this is simply minus I psi bar gamma I del I psi plus m psi bar psi. Now, you know why I have inserted this factor of I here, because I del I, this is a Hermitian operator, right. So, you can write this, the second term is obviously Hermitian, because psi bar psi is Hermitian, psi bar psi is psi dagger gamma 0 psi, which is the Hermitian conjugate of this quantity is equal to itself, because gamma 0 is Hermitian, and then you have psi dagger psi here on the both sides. But in the first term you have psi dagger and gamma 0 gamma I and minus I del I psi. This operator here inside will be Hermitian if this is Hermitian here, right. So, let's just take the Hermitian conjugate of that. It's just minus I will give you a plus I del I psi dagger and then gamma I dagger gamma 0 psi, right. And what is gamma I dagger? Gamma I dagger is I del I psi dagger gamma 0 gamma I gamma 0 and gamma 0 psi. Gamma 0 square is 1. So, this is simply I del I psi bar gamma I psi, and then this will be up to a total derivative. This is just minus I psi bar gamma I del I psi plus I del I psi bar gamma I psi. There is a U1 invariance, and then you can show that there exists a conserved current J mu, which is given by psi bar gamma mu psi and del mu J mu equal to 0. I will not do this for you, and you can construct various quantities like the momentum and so on. You can construct the energy momentum operator, and then you will have the momentum which is given by minus I dq x psi dagger grade psi. The total charge q will be dq x psi dagger psi and so on. What we will study in the following is, we will consider plane wave solutions to the Dirac equations. So, let us do that. As usual, we will consider both positive frequency as well as negative frequency modes. The positive frequency modes, I will denote them by psi plus of x, which will go like u of p e to the power minus I p dot x, and the negative frequency modes I will denote them as I minus of x, which will go like v of p e to the power I p dot x. I will substitute these two forms, and then I will see what, then we will discuss what are the expressions for these spinors u of p and v of p. So, let us consider the Dirac equation. The Dirac equation is given by I gamma mu del mu minus m psi. For positive frequency modes, this will be psi plus equal to 0, and this simply implies I gamma mu times minus I p mu u p minus m u p times e to the power minus I p dot x equal to 0. This simply implies that gamma mu p mu minus m acting on u p equal to 0. Okay. Contraction of gamma mu with various operators will appear quite frequently. I will use the symbol slash to denote contraction with gamma mu. For example, I will denote p slash for gamma mu, p mu, and so on, and del slash for gamma mu, del mu. Whenever I use a slash, it is just gamma mu del mu, and so on. So, this I can write it as p slash plus p slash minus m acting on u of p equal to 0. By solving this equation, we will find the most general expression for u of p. Similarly, if you look for the negative frequency modes, then you will get an equation for v of p. I will summarize these two equations: p slash minus m u p equal to 0, p slash plus m v p equal to 0. These are the two equations obeyed by u of p and v of p, as we can see directly from the Dirac equation, or in other words, these are the Dirac equations for the spinors u of p and v of p. We want to solve these two equations. To solve that, note that if we consider massive fields, then we can go to the rest frame, where the momentum, the 4 momentum p is simply m and 0 in the rest frame, because its 3 momentum is 0 in the rest frame. And we already know these equations are covariant under Lorentz transformation. So, we can solve it in the rest frame, and then we find the solution for u of p and v of p in the rest frame, and then we do a boost to find the general solution in any frame. Okay. So, that is what we will do. In the rest frame, these two equations look like the following. This equation looks like gamma 0 p 0 minus m acting on u of p equal to 0, and the second equation looks like gamma 0 p 0 plus m acting on v of p equal to 0, but since p 0 equal to m, therefore, this implies gamma 0 minus 1 u p again here is m 0 is equal to 0, here again m 0 equal to 0, m 0 equal to 0, gamma 0 plus 1 V of m 0 equal to 0. To solve this, we will choose one particular representation for the gamma matrices, and then the solutions look very simple in this representation, where gamma 0 is 1 0 0 minus 1 and gamma I are 0 sigma I minus sigma I 0. You can see that this set of gamma matrices also satisfy the Clifford algebra gamma mu gamma nu equal to 2 eta mu nu. So, they can be represented for the gamma matrices, the Dirac gamma matrices. In this representation, these two equations have very simple solution. We can see that there are two linearly independent solutions for this equation and two linearly independent solutions for this equation. Gamma 0 minus 1 will have equal to 0 0 0 minus 2, right, 2 times identity. So, this suggests that the linearly independent solution, therefore, gamma 0 minus 1 u m 0 equal to 0 implies there are two linearly independent solutions for u m 0, which I will denote as u 1 m 0, which is 1 0 0 0, and u 2 m 0 is 0 1 0 0. Similarly, you can solve the other equation here, gamma 0 plus 1 v equal to 0. Again, there will be two linearly independent solutions for v, which is given by v 1 m 0 equal to 0 0 1 0 and v 2 m 0 equal to 0 0 0 1. We can find the most general solution, but even without finding the solution in a general frame by performing a Lorentz boost, we can deduce a number of properties for these Dirac spinors u of p and v of p. Now, since there are two linearly independent solutions for u and two linearly independent solutions for v, I will denote them as u r of p and v r of p, where r runs from 1 to. So, therefore, I should clarify this symbol once more. This is a 4 component spinor for r equal to 1 as well as 2, and similarly v r p again for r equal to 1 and 2, these are 4 component spinors. So, we have 4 component spinors, which are u 1 p, u 2 p, v 1 p and v 2 p. Their components, so these are just columns. You have 4 entries for u 1, 4 entries for u 2 and so on. So, I will denote their components by the symbol alpha, beta and so on. So, I have u 1 alpha of p, where alpha runs from 1 to 4 and so on. So, these indices I will denote them as 1 2, and then the components of this u 1, u 2, u 3, u 4 etc., those I will denote by using this symbol alpha. So, you have u r alpha of p for the components of these spinors, and similarly you have v s beta of p. Is the notation clear? Okay. We would like to know what is this relation here, u bar r of p US of P. They are, I mean, as usual, just like here, you can just contract them by the usual the metric eta mu nu and so on. So U alpha is simply eta alpha beta U beta and so on. But these are not raised or lowered, they are raised and lowered. R and S indices are raised and lowered by the unit matrix. So let us look at this quantity here. Okay. This is a Lorentz invariant quantity, because we have already seen earlier that psi bar psi is invariant under Lorentz transformation. When you perform a Lorentz transformation, U, in fact, because they just differ by a number, U transforms the same way as psi transforms. So you get U bar goes to U bar U r bar of P under Lorentz transformation goes to U r bar P S inverse lambda. So this quantity is Lorentz invariant. So you can compute this in any frame, especially we can go to the rest frame and evaluate this quantity here. So this is same as U bar r of M0 U s of M0, and you know what are these U1 U2 already you know from this expression here. So you see, by putting explicitly the values for U bar r and U s, that this is nothing but delta R s. Similarly, you can show that V bar r of P V s of P is equal to minus delta R s, whereas U bar r of P V s of P is equal to 0, which is also equal to V bar r of P U s of P. So by explicit computations and using Lorentz invariance, we have seen that the momentum space, the spinors in the momentum space obey these following relations. U bar r P U s P equal to delta R s, V bar r P V s of P is minus delta R s, V bar r P U s P equal to 0 equal to U bar r P U s P. We will extensively use all these relations later on. Unlike U bar P U s P, this quantity U dagger r P U s P is no longer Lorentz invariant. Okay. So however, we can just use the Dirac equation and then we can evaluate, let us say, this quantity by using the Dirac equation. So let us see what is the expression for this quantity. This is nothing but U bar r P gamma 0 U s P, right. By definition of U bar, this is simply given by this. Now we use the Dirac equation for U s. U s of P obeys this Dirac equation, P slash minus m USP equal to 0. If you take the Hermitian conjugate of this equation, then you will get the Dirac equation obeyed by u bar s of p, and the Dirac equation for u bar is given by u bar s of p p slash minus m equal to 0. So, to evaluate this quantity u dagger r p u s of p, what I can do is that I can use these two equations, and especially for u s of p I will substitute 1 over m p slash u s p, and for u bar s similarly we can do we can write it as u bar s p. So, this is u r bar p gamma 0 u s of p, which is half of the same quantity, this plus u bar r p gamma 0 u s of p, and in the first equation I will write for u s p 1 over m p slash u s, and in the second equation for u bar r p I will write 1 over m u bar r p slash. So, this is nothing but 1 over 2 m u bar r p gamma 0 p slash u s p plus u bar r p p slash gamma 0 u s p. Is this clear? It is straightforward, and this implies you have 1 over 2 m u bar r p anticommutator of gamma 0 p slash u s p, and what is the anticommutator of gamma 0 p slash? Gamma 0 p slash anticommutator is p mu gamma 0 gamma mu anticommutator. So, this is equal to twice p mu eta mu nu, which is 2 p 0. So, what we have got here is this is p 0 over m, which is just a number. So, I can just pull it out, u bar r p u s p. So, this is nothing but u bar r p u s p is simply delta r s. So, you get p 0 over m delta r s. So, to this I can add this relation u dagger r p u s p equal to p 0 over m delta r s. So, okay, so what we did is that we found the solution in the rest frame, and then from using these the 4 linearly independent solutions in the rest frame, we have derived some important identity. What we will do now is that we will find the general solution for u s p in any general frame. This you can do by using 2 ways. First is, of course, you can use a boost, and then you can construct the solution, the general solution for any arbitrary momentum. We will not do that instead what we will do is we will use some identities like p slash minus m times p slash plus m equal to 0. Using this identity, we will construct the most general solution for any arbitrary p. Before that, let me prove to you that this is in fact 0. This is nothing but p slash square minus m square, but p slash square is p mu gamma mu p nu gamma nu minus m square. So, this is p mu p nu gamma mu gamma nu minus m square, but because of the symmetry here you can write it as half p mu p nu anti-commutator of gamma mu gamma nu for the first term. So, this is minus m square, but this is nothing but twice eta mu nu. So, this is p square minus m square, and p square is m square, therefore, p square minus m square equal to 0, and hence p slash minus m times p slash plus m equal to 0. Therefore, if you consider this us m 0 p slash plus m, this quantity is a solution to the Dirac equation, right, using this identity. So, if I denote this to be, if I define us of p slash plus, if I denote us of, if I define us of p to be p slash plus m us of m 0, then this quantity, then this is a solution to the Dirac equation, and for s equal to 1 and 2, there are two linearly independent solutions here for arbitrary momentum, right, because obviously this simply implies that p slash minus m acting on us of p is nothing but p slash minus m p slash plus m us of m 0, and because this is 0, this quantity is 0. So, for any us of this type, it is actually a solution to the Dirac equation. So, therefore, I have two linearly independent solutions for s equal to 1 and 2 constructed from us m 0. Only thing that we need to I need to make sure is that this normalization condition is satisfied, and this will be normalized. If you define us to be p slash plus m divided by square root of 2 m times m plus e, I guess. Yeah, us m 0, then this us is normalized to delta rs. It is normalized such that us p bar ur p equal to delta rs. So, I have the most general solution which I constructed just by using this identity. Similarly, you can construct the solution for Vs of p, which is minus p slash plus m divided by 2 m m plus e Vs of m 0.
Can you just repeat how it's the most general solution?
It's just I mean it's the solution is satisfied for any value of momentum, and then there are two linearly independent solutions, that is all. And you can in fact show that this solution here in fact is they can be obtained by a Lorentz boost from the solution in the rest frame. Okay. Now, what we will do is that I will introduce a projection operator which I will define to be this lambda plus p equal to sum over s equal to 1 to u s p u bar s p. I will show that this in fact is a projection operator, but before that I will explain what do I mean by this symbol. You already know what is u bar u, this is just a number because this is a row, this is a column, and then you can multiply it by using ordinary matrix multiplication. This is number. This product simply can be used to construct a 4 by 4 matrix out of u and u bar, and I define it in terms of its components in the sense that lambda plus p alpha beta. This symbol simply means that its sum over s equal to 1 to 2 u s alpha of p u bar s beta of p. That is all. That is what I mean by this. So, now let us consider this u s of p I already know is given by this, and you can show that this is 1 over 2 m times m plus e times this is p slash plus m sum over s u s m 0 u bar s m 0 p slash plus m. This is straightforward. Okay. Now, what is this quantity here? Again, I can use the definition of this that I have introduced, and it turns out that S u s m 0 u bar s m 0 is nothing but this. So, this in our representation, in the representation that in which we have solved for u s m 0, this is simply equal to half times 1 plus gamma 0. Okay. Good. So, I mean it's very straightforward, right? US because US has the lower two components are zeros. So, only thing that is non-zero is this. So, you have 1 0 1 0 with 1 0 plus 0 1, which is nothing but identity matrix in the first sector, and then all the other things are 0. So, I will use this identity here, then I have lambda plus p equal to 1 over 2 m plus e p slash plus m 1 plus gamma 0 over 2 p slash plus m, and you can use you can simplify this algebra here to show that this is nothing but p slash plus m divided by twice m. Okay. Similarly, I can introduce lambda minus so I leave it as an exercise for you to show that this is just p slash plus m over twice m, and if I define lambda minus of p equal to minus sum over s equal to 1 to 2 VSP tensor with Vs bar of p, then this quantity will be equal to minus p slash plus m divided by twice m. So, from here I get a completeness relation which is lambda plus of p plus lambda minus of p is identity, or if I want to write it in terms of components, then it simply means that sum over s equal to 1 to 2 us alpha p u bar s beta p minus vs alpha p v bar s beta p is equal to delta alpha beta. I also leave it as a homework for you to show that lambda plus acting on lambda plus p acting on up usp equal to usp, that is why it is called as a projection operator. Similarly, u bar sp lambda plus p is u bar sp, and similar relations for lambda minus acting on v. Okay. Okay, so what we did is we constructed the plane wave solution for Dirac equation. So the most general solution of course is a superposition of these plane wave solutions. What we will do is in the next lecture we will take the most general solution and quantize the Dirac field, and then we will see what are the implications of this. All right.